Alright chemists, in this lesson we're going to look at how we can write thermochemical equations, and specifically how we use and obtain these values of changes in heat that we introduced in our last lesson. First, what is a thermochemical equation? Well, let's look at the reaction for the combustion of methane. Remember, that's CH4 plus O2. Combustion is always the oxidation of a hydrocarbon, and it makes, if it's a complete combustion, carbon dioxide and water. Now, that's not balanced. You should tell right away you need 2 oxygens and 2 waters. What do we mean if it's a thermochemical equation? Well, that means we actually have to add the quantity of heat. Combustion reactions happen to be exothermic, so heat is thought of as a product. And you can write just the word plus heat, or plus however many kilojoules there are per, let's say, a mole of this reaction per one of those. But instead we usually write the symbol for the change in enthalpy, and then whatever the quantity is with a positive or negative sign. Combustion reactions happen to be exothermic. There's no rule for looking at a reaction and being able to tell if it's endo or exo, but everyone should know that a combustion has a net release of energy, and that's what that negative symbol means. I'll just make a little note of that the delta H being negative indicates this is an exothermic, which means heat is produced overall. This is the net change in enthalpy. There's always some energy absorbed and some energy released. What we're showing here is the net amount. So how do we use values like this delta H to do stoichiometry problems? Well, let's take a look at this combustion reaction itself, and here we say what amount of heat is released when 5.8 grams of methane burns. Well, let's start with that 5.8 grams. If you don't know what to do, convert grams into moles. There's 16 grams of methane underneath 1 mole of methane. How do I get into this kilojoule per mole of reaction? Well, a mole of reaction is just one of these balanced reactions. So the coefficient of methane is 1. So for every 1 mole of methane, you actually have 1, we'll say, mole of reaction. It's a little redundant here because the coefficient of 1 is there, but if it's not, that's a useful conversion factor to include. And then we can say for every 1 mole of reaction, there's negative 890 kilojoules involved, because that value goes with the whole thing, and we're trying to isolate it down into just what happens with methane. So you plug the numbers in and you round to 2 significant figures, you get negative 320 kilojoules as an absolute amount, no longer per mole. And that negative sign means heat is released. So you could actually say 320 kilojoules is released, and it would imply the same thing as including it with the negative sign. Okay, so I'd like you to hit pause and try the one right next to it. This is for a different reaction with a different delta H value. This time they're giving us the heat, and they want to know the mass of one of the chemical species. Try that now. All right, so we're releasing 25 kilojoules, so I'm going to actually start with a given negative 25 kilojoules. And then in my first conversion factor, I'm going to put kilojoules in the denominator, so negative 850 kilojoules is how much is released for 1 mole of reaction. And then in 1 mole of reaction, in other words, 1 reaction, we're trying to get into stuff related to iron. There's 2 moles of Fe, 2 moles of iron. And then to get into mass of iron, for every 1 mole of iron, I have 55.85 grams of iron. And you can just check your dimensional analysis. The kilojoules cancel, the moles of reactions cancel, and the moles of iron cancel. We are just in grams. And notice those negatives cancel, so you'll get the expected positive value. Turns out to be 3.3 grams of iron. That's how much we would produce in this what's called thermite reaction, which is a well-known reaction of aluminum and rust to make elemental iron. It's a notoriously hot reaction. You're taking solids, and it's so exothermic that the iron produced is molten. It's liquid hot iron. If you've ever seen pictures or videos of steel factories, this is what that glowing orange liquid is. It's so hot that the iron is liquid and actually gives off light. Okay, so that's how we use those delta H values. How do we get them? How do we get these things for a chemical reaction? In our first lesson, we looked at doing indirect studies with calorimetry, but there's other ways to get these delta H values for reaction that involve using reference values, such as the delta H of a known reaction, or what's called a heat of formation, or using bond energies. So those are the three ways we're going to cover right now about how we use pieces of reference information to get the heat of a reaction. The first one is called using Hess's law, which states that the value of delta H for a reaction is the same whether we treat it as one reaction or as the sum of several reactions. This was developed by Germain Hess and applying the concept that delta H is a state function. Two things to know: the sign of the value changes if the reaction is reversed, and we multiply delta H by a factor if the coefficients change. You'll see what we mean when we do this right now. So let's look at the first example. This is taking these three reference reactions and trying to manipulate them to get the one we want. How I do this is I just look at the reaction left to right, and I go through each species and figure out where it shows up above, and then I manipulate those reactions respectively to get the chemical species in the right spot with the right coefficient. For example, the first thing I see is 2 nitrogens as a reactant. And I've got a third reaction up here that has nitrogen as a reactant, but it's got the wrong coefficient. I need to make this a 2, which means I actually have to multiply this whole reaction by 4. Well, that means I'm going to multiply my delta H by 4. So I'm just going to write times 4 right next to the delta H. What that does is that changes that third reaction to become 2 nitrogens plus 6 oxygens plus 2 hydrogens to make 4 nitric acids. Same molemole ratio, just bigger coefficients, and therefore a bigger delta H value in magnitude, and that will take care of the nitrogen. I'm going to skip oxygen for a second because it shows up in multiple places, and instead look at dinitrogen pentoxide, which only shows up in the second reaction. It's got the wrong coefficient and it's on the wrong side. I need to double this and get it to the other side. So that means I need to multiply this reaction by 2, but I also need to reverse it. So I'm going to negate that delta H value. And when I do that to the reaction, it becomes 4 nitric acids, turns into 2 dinitrogen pentoxides, and 2 water molecules. That takes care of those two things. All that's left is the oxygens and some other things that we have that are sort of along for the ride but can't be in the net reaction. For example, the water. So let's look at that. It's now got 2 in front of it, and it's on the product side, and I see water in only one other spot. It's in the first reaction. I need to get it on the reactant side and double it. So that means the first reaction also has to be multiplied by -2. So let's do that and write the outcome. That's going to make the first reaction turn into 2 waters, decomposes into 2 hydrogens, and 1 oxygen. And look what happens. Now we have these 3 reactions, and if we add them together, the 4 nitric acids produced cancel with the 4 nitric acids formed, the 2 hydrogens reacted cancel with the 2 hydrogens produced, and those 2 water molecules are also gone. We're left with some oxygens, but we do have a net amount of oxygen. That 1 oxygen product will get rid of 1 of those oxygen reactants, so we have 5 left over. We also have 2 nitrogens, and we have 2 nitrogen pentoxide, which is exactly what we want. So now we can simply add up those reactions now that we've manipulated their delta H values, and when you do that, you get a numerical value of 28.4 kilojoules per mole of reaction. And I'll just put a box around that. So, there's one other to try right next to it. It's the same concept. We've got a different reaction here. We've got 6 carbons plus 6 hydrogens and 3 oxygens makes a glucose molecule, and 3 reference reactions up above. I want to see if you can do this one, but also a little bit faster. See if you can skip the rewriting the reaction part and just figure out what you have to do to those delta H values to get the one that you want. Try that now. Okay, let's see how you did. So, reading the reactants and products left to right, the first thing I see is carbon. Only shows up in the first reaction. It's on the correct side, but I need 6 of them. So I'm going to multiply the first one by 6. Hydrogen also only shows up in one spot. It's in the second reaction. It also needs a 6. And I know that what I'm doing is correct because if the species I'm considering only shows up in one place, I don't have to worry about what else is happening to the rest of that reaction. I know it's going to work out as long as I do it correctly, and we'll be left with what we want. I am going to skip oxygen because it shows up in every single reaction, and that's just harder to keep track of. But I'm going to look at glucose, which only shows up in the third reaction. It's got the correct coefficient, but it's on the wrong side, so it needs a -1. And there we go. I've figured out exactly what I have to do to all 3 of them, so it should work out when I add up the math, and if I were to combine the reactions. You would get a delta H of -1273.02 kilojoules per mole of reaction. So that's how you use Hess's law to figure out the delta H value for a reaction given the delta H's of other reactions. That's the first way. The second method to get delta H is involving what are called heats of formation. These are tabulated values, and you have a big list of them in the back of your workbook that shows these formation values at what's called the standard state. That's what that superscript 0 refers to. The standard state is a defined set of conditions, specifically 25 Celsius and 1 atmosphere. And by definition, the heat of formation is how much enthalpy is involved in forming specifically 1 mole of a compound from its elements. So we could imagine making a compound like methane from elemental carbon and hydrogen, a compound like water from elemental hydrogen and oxygen, etc. The coefficient of the product has to be a 1, always. And that's why we sometimes see fractions in the reactants. And the elements are whatever that element would be in its standard state. So gaseous oxygen, solid carbon, gaseous hydrogen, etc. And these have numerical values, and they're given in tables. So I could actually just plug them in if I looked them up. The heat of formation of methane is -74.6 kilojoules per mole. The heat of formation of water is a bit more in magnitude, -241.8 kilojoules per mole. And the heat of formation of carbon dioxide is -393.5 kilojoules per mole. Just looking those up from the table that you have in the back of your workbook or anywhere else, frankly. There's lots of sources of these heats of formation values. What's the point? What do we do with these? Well, there's a boxed equation to your right that says the change in enthalpy of a reaction is essentially all the heats related to the products minus all the heats related to the reactants, the sum of those, where each one is multiplied by whatever its coefficient is in the reaction. So here's a chemical reaction that uses those compounds up above. So I know that the heat of formation of methane, I'm just going to rewrite them below each substance, left to right. Methane is -74.6, CO2 is -393.5, and water is -241.8. You'll notice I skipped the oxygen. Well, elements don't have a heat of formation. You can't form an element in its standard state because The heat of formation is, by definition, a compound from an elemental form. So it doesn't take any energy, by definition, to form an element in its standard state. We're not talking about forming it from its subatomic particles. This is a definition that chemists use to manipulate compound formation values and get delta H's. So then the delta H of this reaction would be the products minus the reactants. So I'm going to take negative 393.5. I'm going to multiply it by 1 because it has a coefficient. And then negative 241.8 multiplied by 2 because of its coefficient. And then I'm going to subtract everything related to the reactants, which in this case is just the methane. So minus the methane, negative 74.6, and then times 1 for its coefficient. You do the math, and you get negative 802 kilojoules per mole of reaction, which is actually not too far off, at least in order of magnitude, compared to the values that we were using before. I know it's off by a good 88 or so kilojoules, but that means that wherever this number came from is a different source of reference information. These don't always give you exactly the same numerical value in the end. It depends on the precision and accuracy of these different numbers that we're getting from reference sources, and they all mean different things. Heats of formation are typically very reliable, though, in terms of getting these values. You get a pretty accurate, pretty close to the right value. So that's how we use heats of formation. I want you to try. Here's one written in words. If you don't know what liquid methanol is, it's CH3OH turning into methane and oxygen. Looks like I would need to balance that by putting a 2 in front of the methanols and the methane. So look up what the formation values are for methanol, methane, and oxygen. Hopefully you know that's 0. And then see if you could get the delta H for this and come back and check to see how you did. Okay, so liquid methanol has a value of negative 238.6. And methane we already have from before, negative 74.6. And oxygen is 0. So delta H is the products, 2 times negative 74.6 plus 0, minus the reactants, 2 times negative 238.6. And we get positive 328, I'll just leave it at a whole number, kilojoule per mole of reaction. Okay, so that's how we use heats of formation to get delta H's of reactions. It might not look like it, but this technique that we just did is actually an application of Hess's law. We're actually just manipulating these chemical reactions and multiplying coefficients by these whole number values, or sometimes negative fraction values, and getting a delta H out of that. So it actually is just Hess's law in disguise. The third and last thing we're going to look at today is very different. This uses bond energies. This is frankly considered to be the least accurate method, but in the absence of anything else, it's a good go-to. And it's an excellent reminder of the concept of what happens when a chemical reaction occurs. Since we're talking bond energies, that means we need to talk about bonding and look at the bonding that breaks and the bonding that forms for any chemical reaction. So here's a methane with 2 oxygens turning into 1 carbon dioxide and 2 water molecules. Hopefully that wasn't too fast to show what those structures look like. And anytime you have a chemical reaction, there's always energy going in to break bonds, and there's always energy coming out to form bonds. And every time you break a bond, energy is absorbed. Every time you form a bond, energy is released. By definition, that's true. All we get is the net change. So if we have tabulated bond energies, which is why this method is not always accurate, because bond energies are not absolute. They depend on what type of molecule that chemical bond is in. Not all OH bonds are created equal, for example, but we can get a rough approximation of it. Then we can use these bond energies and figure out what the delta H should be, roughly. So if I think about what bonds are broken, that just means I need to consider breaking every single thing in the reactants. Well, we broke 4 CH bonds, and those were 414 each, if I use the table that's off to the right. We also broke 2 oxygen-oxygen double bonds. Those are a bit stronger, 498 kilojoules per mole each. And then we formed 2 carbon-oxygen double bonds, which are 715 kilojoules per mole of bond each. And we formed 4 OH bond at 464 each. So there's everything I broke and everything I formed. We could even highlight it a little bit. Those CH4 bonds, there's all 4 of them right there. Those OO double bonds, that's what they're worth right there. The CO doubles, there's 2 of them. And then we have the OH bonds, 4 of them at 464 each. So you can see how we get all those things tabulated together. Then you do the math, and we get, luckily, a negative number. So it's at least accurate enough that it gives us a negative number. I only get negative 634 kilojoule per mole of reaction for this, which is quite far from all the other values we've seen for the methane combustion, but it gives us a good approximation of what it might be in the absence of everything else. So that's how we use delta H values to look at stoichiometry problems and quantify heat related to how much mass or mole of something is reacted or produced. And then those are the main 3 ways that we use reference information to determine the delta H of a reaction: Hess's law, heats of formation, and bond energies. The first 2 being very similar, the third one being very, very different.